Hello everyone, welcome to our channel. In today's session, I'm going to discuss the design of beams. So first of all, let us see the design steps. First of all, we calculate the maximum bending moment, and our formula is for UDL, that is uniformly distributed load. Our formula is WL square by 8, and for point load WL by 4, where W is the given load, L is the length. Then we'll calculate the factored BM, that is 1.5 into this bending moment. Then in step 3, we calculate the maximum shear force, that is V, that is WL by 2 for UDL, and for point load it is W by 2. Then we'll calculate the factored shear force, VU, that is 1.5 times of this shear force. So here I have given the formula for both UDL and point load. So whichever is given in the question, you can use that formula. Then we'll calculate this MD, that is the factored bending moment, from this clause 8.2.1.2 of the IS 800-2007, and this is our formula. So this thing I'll show clearly with the help of a numerical. Now first just we'll see the steps, and in the code you'll find that the value of beta B, this is 1.10, gamma MO is 1.10 from table 5 page 30 of the IS code. And putting all these values, this MD we have calculated here, then this we have in the code jet, FY you will get it, then gamma MO. After putting all the values, we'll get the value of this jet P. After that, from the IS code in page 137, we have a table. From there, what to do? We'll find one section such that the jet P from that section is greater than the jet P we have found out, because we are doing the design here. So from this jet P, whatever we have got from a value greater than that value, we'll take from the code, and from that value we'll get the section, and we'll write down the properties of the section. And then from this table 2 of the IS 800-2007, we always consider roll section. Then we'll calculate B by TF. This value should be less than 9.4. Then it will belong to class 1. And if this one is less than 10.5, then the section will belong to class 2. This in numerical only you will understand. And if these are not found, generally we check for class 1 and class 2. And if we do not get this 2, then we'll check for other class. It's already given in the code. Then with this formula, epsilon equal to root over 250 by Fy, we'll find out the value, and we always assume that the neutral axis is at mid-span, that is of the section. After that, these things are already given in the code. Then we'll find out d by tw, and it should be less than 84 epsilon. And this d, the formula for this d, it is h minus 2 into TF plus R1. This TF and R1 will get from the steel table. After getting all the values, the condition for the section to be plastic will be satisfied. Then in step number 7, we'll check for bending moment. So again we'll use the same formula which we got. Now this jet P value, we'll use the new value which we have taken from the table. Other rest value will be same, and we'll find out MD. And the value of this MD should be greater than the MD which we have calculated in step number 2. After that, we'll check for shear force. We'll use just see clause 8.4 of the IS 800-2007, and we'll get this formula from the code. Now AV is our area, and it is equal to H into TW, and this FYW is equal to our FY only. Then VM is equal to our VP. And then we'll now check 0.6 VM. So actually what we'll do here, this AV and FYW, if you put the values, we'll get the value of VP, and this VP will be equal to VM. And then we'll find out 0.6 times of VM, and it should be greater than VD, which we have calculated in step number 4, that is our factored shear force. This value should be greater than VD, then our section will be safe. Then in step number 9, we'll check for deflection, the maximum deflection. So for point load, our formula is W L cube by 48 EI, and for UDL, the 5WL to the power 4 by 384 EI. So whatever load is given in the question, accordingly we'll use the formula. Now here this E is our Young's modulus, and the value is 2 into 10 to the power 5 Newton per mm square, and I value will get from the steel table. Now we'll go to table 6 of the IS 800 2007. There you will see there are many conditions. So we'll consider the condition other buildings, live load for floor and roof. This in numerical I'll show you clearly. So for other buildings, live load for floor and roof, we need to find out span by 300. So span will be, that is our L, which is already given in our question. So this value should be greater than our this maximum deflection. If it is greater, then our section is safe. Now let's see clearly with the help of a numerical. The question given to us is a simply supported beam of 6 meter span. 6 meter span means this is our L, 6 meter. We'll convert it to mm, that is 6000 mm. Carries an UDL of 40 kilonewton per meter. So UDL is given as 40 kilonewton per meter. This is our W, and a point load of 30 kilonewton, and point load is given as 30 kilonewton. This is also W. Now see, in this question I have shown you both UDL and point load. So in your question, either UDL or point load, if any one is given, just use any one of the formula. If both are given, use both the formula and then add it at midspan. Next, design the beam. So here clearly it is given to design the beam, reaction and check for shear and deflection. That means you have to check everything. The beam is laterally supported. Take Fy equal to 250 MPa. So this is directly given that Fy is 250 MPa, that is 250 Newton per mm square. And E, that is Young's modulus, is 2 into 10 to the power 5 Newton per mm square. So this is the given. Now first we'll go to step number 1. The formula was for maximum bending moment. It is, this one is for UDL WL square by 8, and this is for point load WL by 4. So for UDL our W is 40, this L is 6, then this is it. Okay, and for this point load our W is 30 and L is 6. So we'll get the value as 225 kilonewton meter. In step number 2, we'll find out the factored bending moment, that is MD, which is equal to 1.5 into M. We'll get the value as 337.5 kilonewton meter. If we want to convert it into Newton mm, then it will be into 10 to the power 6 Newton mm. Next, in step number 3, we'll find out the maximum shear force P. That this formula is for UDL WL by 2, and for point load it is W by 2. We'll add this 2, we'll get the value as 2400 kilonewton. Then in step number 4, we'll find out the factor shear force VU, which is equal to 1.5 times of the shear force. So we'll get this as 3600 kilonewton. Then in step number 5, from clause 8.2.1.2 of IS 800 2007, we'll use this formula. So I'll show you this. Yes, it is clause 8.2.1.2. This is our formula. This MD is our factored bending moment. This beta BC, this is 1.0. Then ZP will find out. Fy is given to us, and gamma MO, you know it is from table 5. So putting all the values, we'll get the value of ZP as this will come in mm cube. So if you convert it into centimeter cube, we'll divide it by 1000. So we'll get this as 1485 centimeter cube. Now in step number 6, we'll go to table 46 of IS 800 2007, and we'll take a section such that the section has the value of ZP greater than this ZP which we obtained. So see here our ZP was 1485 centimeter cube, and we have taken the section such that the ZP is 1533.36 centimeter cube. And we'll convert this into mm cube by multiplying it by 1000. So now see, this ZP is greater than this ZP, and the section which we have taken is ISMB 450 at the rate 72.4 kg per meter. So you take out page 138 of the IS code. Now see this ZP, that is plastic modulus, this is the column. So now see, I have taken as 1533.36. so this is our ZP, and corresponding to this ZP we have the section, and our section is ISMB 450 at the rate 72.4 kg per meter. So this is the section. You just refer to your IS code and you can see it clearly. Then from there we'll get the properties. The width of flange BF is 150 mm, and small b will be our BF by 2. So you calculate it. Then we have thickness of flange TF as 17.4 mm. And the same section we'll get it in our steel table also. So you can take page number 12, table 4 of the steel table to see the section. Wait, I'll show you. This is the section ISMB 450 at the rate 72.4. So this is our BF. These are the different values which you will get. This is the column IXX, IYY, this is the column, and R1, this is the column. So from here you will get the value of R1. So this R1 is 15 mm and TW, thickness of web, is 9.4 mm. Now you just refer to table 2 of IS 800 2007 and find out the value of B by TF, and it should be less than 9.4, and yeah, our value is less than 9.4, it is 4.31. So our section is class 1 plastic. Then again we'll consider that the neutral axis is at midspan. So first of all we'll find out the value of D using this formula. These values we already got from the steel table or from the IS code. Now putting all the values, we'll get the value of D. After getting the value of D, we'll find out D by TW, and it should be less than 84 epsilon. So epsilon you know, which is equal to root over 250 by Fy. Our here the value will be equal to 1. So putting the value, we'll get this value of D by TW as 40.97, which is less than 84 epsilon. So this will be our class 1, and the condition for the section to be plastic will be satisfied. Now see this table 2, I'll just show it. You can see your IS code. Now see, we'll consider it as roll section B by TF. It is less than 9.4 epsilon. This is class 1 plastic. Otherwise this is class 2, this is class 3. Then we have considered neutral axis as mid depth, and D by TW we have found out this is 84 epsilon, that is class 1 plastics. So both the conditions for class 1 plastic is satisfied. So our section is class 1 plastic. Then in step number 7, we'll check for the bending moment. The same formula we'll use for MD. Now this time this BB we know it is 1.0. This ZP is the new ZP of the section which we have taken, 1533.36 into 10 to the power 3, because we are converting it to mm cube. Then Fy it is already given. Gamma MO is 1.10, which is given in table 5. If you have seen my previous lectures, this thing I have shown again and again clearly. This table 5, how we'll get this value of gamma MO. Now after that we got our bending moment as 384.49 kilonewton meter. Actually we'll, after solving this, we'll get the value in Newton mm, and then we'll divide it by 10 to the power 6 and we'll get the value in kilonewton meter. And this is greater than 337.5 kilonewton meter, and this value is the factored bending moment MD, which we have calculated in step number 2. So since it is greater than the calculated BM, so our section is safe. Then in step number 8, we'll check for shear force from clause 8.4 of the IS code, and the formula is this. See this 8.4, the formula is VP equal to AV YW by root 3. So this is our shear area. Now see, the value of the shear area we have taken is equal to H into TW. Why? Because our section is rolls section, and this FYW is equal to Fy. I already mentioned this in the step, and this Vn is equal to Vp. So in this way we'll get the shear area H into TW. We'll put the values and we'll get the value as 4230 mm. Then FYW is equal to Fy, that is 250. So putting the values, we'll get the value of Vp. And Vp we calculated as 610.54 kilonewton. Then already it is given in the code, Vn is equal to Vp. So Vn will also be 610.54 kilonewton. Next we'll find out 0.6 times of this Vn or Vp. We'll get the value as 366.32 kilonewton, and this is greater than 202.5 kilonewton. 202.5 kilonewton is our factored shear force which we have calculated in step number 4. Since our now calculated value is greater than the given one, so our section is safe. Then in step number 9 and the final step, we'll check for deflection. So maximum deflection, this is our formula for point load. So first we'll calculate the value for point load. W, L, E, everything is given, and I we have found out from the steel table. You can check it out. So putting all the values, we'll get the value of the maximum deflection for point load. The value we have obtained as 2.22 mm. So we'll keep this in mm only. Then maximum deflection due to UDL. This is the formula. This already I gave in the steps. So putting all the values, we'll get the value as 11.10 mm. Now total deflection, will sum up this 2.22 and 11.10 and we'll get this as 13.32 mm. After that, just refer table 6 of the IS code. Just considering other buildings, live load for floor and roof, span by 300. Our span was 6 meter, that is 6000 mm. So this is the value. This is our table 6 deflection limits. from the IS code. See, here we have other buildings, floor and roof. This is span by 300. This condition will calculate. And this value is 20 mm, which is greater than our 13.32 mm. That means this calculated deflection. So it is greater than the calculated deflection. Hence, our value is safe. Thank you very much for watching the video. If you liked the video, don't forget to like, share, comment, and subscribe to our channel for further notifications.